forward from our previous work that we have already done. Uh, in the last lecture, we just saw that we had a relationship between the number of trunks and the traffic in Erlangs while keeping a certain grade of service B at 0.002, and we compared different graphs for different values of availability. As we move away from full availability scenario, the curve becomes steeper and steeper. Now, let's see. In this, this is basically the curve that I'm talking about that we have already studied in our last lecture. This is just for a review, and so that we can move forward. Now let's move on to our next slide. And now we need to find out the traffic capacity of different types of gratings. For ideal grading, each outgoing trunk carries equal traffic. If we have a amount of a lengths of traffic and we have got n number of trunks, then the occupancy of each trunk would be a over n. If we assume that each trunk is being busy is an independent random event, then the grade of service B would be equal to the occupancies of, we can multiply the occupancies of each and every trunk. So we multiply A over N, which is the occupancy of one trunk, and we keep on multiplying K times, because K is the availability of the system. The number of trunks required to carry A lengths of traffic with B grade of service would be, from this very equation, we can derive that N is equal to A into B raised to power 1 over K. This is an this is the Erlang's ideal grading formula. But if we have N greater than or equal to K, then A would be equal to A raised to power K plus N minus K into B raised to power 1 over K. Using this equation, we can solve the example 5.2. I would recommend you to go to pages 125 and 126 and solve this example 5.2. If you have got any problem in solving it or understanding it, we can discuss it after this lecture or on Friday when we have a review meeting on this. Secondly, as we move forward, let's see, we'll go up to the link systems. We can refer it back to our chapter number 3 of this book, and I would recommend you to go to figures 3.15 and 3.16. Those would give you a little background on this system also. Here you can see basically a two-stage network. Now we'll see what happens if we do not have a single stage network and we have a two-stage network. And we'll see if the availability of the system is affected or not, or how does it work for us. We can use a 4-group homogeneous grading for at the first stage to implement the system. Let's see what happens if we have two stages. You can see in this figure above that we have got one stage which is here and another stage which is here. and each of these stages have sub switches in it, and each has its own inlets. The total number of inlets here is 100, and the total number of outlets in this complete system is 100. Total number of outlets is 100. So, and if there are totally 100 inlets, it means that the total number of switches in the first stage, which we call A switch, would be 10. So we have 10 switches in A stage and 10 switches in B stage. Now we connect or link these two systems or link these two stages to make a two-stage network. And we have a restriction that one of the sub switches in stage A can only connect to one of the sub switches of stage B. If we have got one link over here, another link from this to this is not possible. This is not possible, so I put a cross on it. So there would be the next link would be from this switch, or the second outlet would go to this second switch, third outlet would go to this third and fourth and so forth. So all the 10 outlets will connect to 10 different switches. In this way we have a connection, but this is not a successful system, because a two-stage network would create blocking or mismatch. It would create mismatch, and the probability of blocking would be very high, because if a user from this side wants to connect to a user on this switch, it can get connected. But if a second user from this side comes and wants to go to this to another user on this side, it is not allowable. It creates blocking. So it has only a space, only the capacity to go to another switch, 9 different other switches, which is useless in this situation. So this is not a successful system. So two-stage networks are not used anywhere. Now let's see what is conditional selection. In a multi-stage network, it is possible to encounter stage congestion at later stage also. So conditional selection is used, that is, a marker does not set up a connection until it has checked the busy or the free status of the outgoing trunk. Unless it knows that the outgoing trunk is free, it won't initiate the connectivity, and it will start giving a network not available message. For example, in a simple telephone system, how would it do? It would give a network not available tone to the caller. Now let's see what would happen if we have a two-stage network, and how many cross points would it contain. Although I have already told you that a two-stage network is not a practical system, but we need to calculate the number of cross points in this system, so that it is easier for us to understand the calculation of cross points in 3-stage, 4-stage, 5-stage networks. Let's suppose the total number of inlets of the system is capital N, and total number of outlets in the system is capital N. So N is inlets and N is the number of outlets. The primary switches have small n number of inlets and secondary switches have small n number of outlets. So the number of primary switches would be the number of secondary switches, and that would be equal to the number of outlets per secondary switch, because each secondary switch has to get connected uh, to each of the primary switch. So the number of inlets per secondary switch would be G equal to capital N over N. Number of cross points per primary switch would again be equal to the number of cross points per secondary switch, and that would be equal to G multiplied by N, small g multiplied by small n. Why is it so? You can see from the diagram that we have got N inlets and G outlets. G is the number of secondary switches. Similarly, on the secondaries, on the B stage side, what happens is that we've got G number of inlets because we have got G primary switches, and we have got N number of outlets per secondary switch also. So each switch, whether it is on the primary side or it is on the secondary side, both of these have cross points equal to G into N. So G into N is also equal to capital N. How do we come to this conclusion? Because G is the number of primary switches, N is the number of inlets per primary switch. So when we multiply with it, we get capital N. So the total number of cross points in a two stage, this 2 represents, when we write C2, it means that we have got a two stage network. It would be 2 into G into N. So it would be 2 into, you can say, we can replace G into N by N square over N. Since there is one link between each primary and secondary switch, number of links is equal to number of primary switches multiplied by the number of secondary switches. This is the number of primary switches, this is the number of secondary switches. Number of primary switches is G, number of secondary switches is G. When we multiply both of these, we get G square. And what is G? G is equal to capital N over N. So what we do is that we multiply capital N over N by capital N over N. So we get G square. This gives us the number of links in such a system. If the number of links is equal to the number of incoming and outgoing trunks, then G square, which is the number of links, that would be equal to capital N. What this would ensue, it would give small n equal to under root n. This is very simple arithmetic that we can use to find to derive from our previous equation. So the total number of cross points would be C2 equal to 2 into capital N raised to power 3 over 2. Let's see this example 5.3. We've got 200 incoming trunks here and 200 outgoing trunks. On the primary side, or the on the stage A side, we've got 20 switches with each of the switch having 10 inlets, while on the secondary stage, or the B stage, we have got 10 switches with each of the switch having 20 outlets. So we have got 20 switches on the A side and 10 switches on the B side. So if we multiply 20 by 10, we've got 200 links. Now, let's see what happens. How can we define and find the value of cross points in such a system? In B side, we have just flipped it uh, uh, and reversed it. For example, what we have done is that on the stage A, we have placed 20 by 20 switches. 20 by 20 means 20 inlet and 20 outlet. 20 inlet and 20 outlet. These are switches. And we are using 10 of such switches. Similarly, we use 10 by 10 switches, which means 10 inlets and 10 outlets switches per sub switch on the B stage, and we have got 20 such switches in this case. If we multiply the number of switches by number of inlets over here in the A stage, we get 200. If we multiply the number of outlets, which is 10, and multiply it with the number of switches, which is 20, we get 200. Now let's see what would happen if we have got a three-stage network. A three-stage network would have a pair of sets of links. One would be called the A links and another would be called the B links. In this case, again, we are assuming capital N number of incoming trunks and capital N number of outgoing trunks. If the number of inlets per primary switch is small n, and what would be the number of primary switches? It would be capital N divided by small n, and we call it G1, which is the number of primary switches. Similarly, on the tertiary side, we call this the primary stage. This is the secondary stage, and this would be the tertiary stage. On the tertiary stage, how can we find out the number of switches? We've got n number of outgoing trunks, and each of the sub switch has small n number of outgoing trunks. And if we divide capital N by small n, we get G3, which is the number of tertiary switches. Now, what is the number of secondary switches? How can we find that out? Symbolically, it is G2, which is the number of switches on the secondary stage. Here, the number of inlets here are capital N over N, which is the number of primary switches, and number of outlets per switch is again capital N over N, because capital N over N is the number of the tertiary switches. So one sub switch on the secondary side will have capital N over small n inlets and capital N over small n outlets. Now the question is, what is the number of secondary switches, and how does it affect our system or the performance of our system? As we have already assumed in the two-stage networks, there is one link from each primary switch to each secondary switch, and one link from each secondary switch to each tertiary switch. The probability of being unable to set up a call due to blocking is very less as compared to two-stage networks because we have got an alternate path also. In the two-stage network, If a user from first primary switch or the topmost primary switch is connected to the top most primary switch, topmost secondary switch, uh, then another user who comes in would not be able to connect to a customer or to a user on the same top sub switch on the B stage. While in a three-stage network, this situation is improved. How? Because from the secondary switch, we can we can have an alternate path to the tertiary switch and to a customer connected on the third stage. So, three-stage network is far more improved as compared to a two-stage network. Consider a three-stage network with capital N incoming, and I've already discussed all the things. If the number of secondary switches is taken as G2 equal to capital N over capital N over N, because which is also equal to the number of outlets per primary switch and also equal to the number of inlets per tertiary switch. How did we do that? We have divided capital N. We are considering N outlets, and we have got capital N over N outlets per secondary switch. Capital N total number of outlets and capital N over small n is the number of outlets per secondary switch. You can map this on the primary side also, because the total number of primary switches, primary inlets is capital N, and if we divide it by the total number of inlets to the secondary or to one of the secondary switches, which is capital N over small n, again we get small n, and this small n is also equal to the number of outlets per primary switch and also equal to the number of inlets per tertiary switch. Number of cross points in the primary switch would be n square into capital N over n. What is capital N over n? It is the number of primary switches, and if we multiply it with the we have to multiply it with the number of cross points per primary switch. What would it be? It would be n square, and if we get a value of small n into capital N. The number of cross points in the secondary stage would be small n into capital N over n whole square. You can see this from our previous slide, and you can confirm this from our previous slide also. So the total number and the number of cross points in the tertiary switch would again be equal to that in the primary stage, which is n square into capital N over n, and we get small n to n into capital N. So the total number of cross points would be, we can add these three up, small n into capital N plus n square over small n plus small n into capital N, and we get capital N into 2n plus capital N over n. How can we get the minimum number of cross points in this situation? We differentiate the above expression with respect to small n and equate to 0. This equation that we are talking about, this is the number of cross points. We differentiate it with respect to small n and equate it equal to 0. And what we get is n is equal to capital N over 2 whole under root. If this is the case, then what we can have, putting this value of small n, we can have C3 is equal to 2 into under root 2 into n raised to power 3 by 2. And if we compare it with the number of cross points with the stage network, which is C2, we can have it is 1 under root 2 times C2. And if we compare it with the single stage network, we get 2 raised to power 3 by 2 into n raised to power minus 1 by 2 into C1. This is simple arithmetic derivation. Now let's see what would happen if we have a single stage concentrator. A concentrator is a switch in which the number of primary inlets or the number of inlets is more than the number of outlets. Similarly, we have a three-stage network. On the primary stage, all the inlets are getting connected, and the total number of inlets, we say it is capital N, a capital M, and the total number of outlets is capital N. Then each primary switch has small m number of inlets, and each tertiary switch has small n number of outlets. So the number of primary switches would be capital M over small m. Number of tertiary switches would be equal to capital N over small n. Suppose there are G2 secondary switches. G2 means the number of switches in the secondary stage. What happens?